Hey everyone, thank you for coming and thank you for giving me this opportunity to present to you all. My name is Andrei Bondarev and the name of his presentation is Catching the AI Train. A little bit about myself. I fell in love with Ruby about 13 years ago. I've built software, I've built and led teams in the federal government, in the SaaS consumer product and B2B enterprise verticals. I currently run a software development firm and play a role of either an architect or a fractional CTO, depending on the type of project we work with. And this year I built a Langchain.rb library, which is a Ruby library to build LLM applications. We'll cover it in this presentation. So, can we ignore the AI train? I don't think it would be controversial to say that Ruby is behind some of the other languages when it comes to its AI, machine learning, data science capabilities, libraries, and knowledge. And this might be the largest ongoing revolution in software development, at least in my memory. We largely ignored the massive push to microservices and service-oriented architecture. We partially brushed off the complicated JavaScript front ends and its tooling. We skipped the whole blockchain trend. We as a Ruby community survived, but this time might be different. According to the McKinsey and Company report, generative AI's impact on productivity could add the equivalent of $2.5 to $4.5 trillion in value to the global economy. 75% of the value delivered will be across four areas: customer service, customer operations, marketing and sales, software engineering, and R&D. Generative AI will be automating work activities that take up to 60 to 70% of employees' time today. Half of today's work activities could be automated between 2030 and 2060. I suggest everyone reads this private equity's Code2 AI report. They have a slide where they're making a claim that the AI models will be the centerpiece of all of the modern tech stacks. So essentially, we as the application developers in the application layer, we're going to be building on top of these AI models. So why Ruby, or why not Ruby? The Ruby community has so much passion for this language. I think the monoliths are back in fashion in this environment of economic stagnation or economic contraction, depending on who you ask. The monoliths are very attractive. The leadership is evaluating all of its costs, and the microservices architecture is very expensive to run, and the monoliths is a good alternative. The Ruby community is very pragmatic. We hate reinventing the wheel. The whole notion of there's a gem for that. I find that seasoned Ruby developers have a really good grasp of sound software development fundamentals, unlike some of the other folks coming out of academic or research backgrounds. And Ruby is very similar to Python. It's another high-level language. It's also written on top of C. In the instances where Python libraries wrap C functions, I think we should be able to build a lot of those Ruby libraries ourselves as well. In fact, Andrew Kane probably built a good amount of them already. So what is generative AI anyway? Generative AI is a type of artificial intelligence technology that can produce various types of content, including text, which is what we're going to focus on in this presentation, imagery, audio, video, etc. Large language models are deep learning artificial neural networks with general purpose language understanding and generation. They exploded in popularity after the Attention is All You Need research paper that came out in 2017 that introduced the Transformers architecture. We're not going to be covering Transformers, unfortunately. So the LLMs excel at a lot of different tasks. Some of the tasks they're really good at are structuring data, so taking and converting unstructured data to structured data. They're great at summarizing data, taking large bodies of text and producing summaries, and also classifying data. So taking blog posts, a list of blog posts, for example, and bucketing them into technology, sports, or business topics, etc. And LLMs are great at a lot of other tasks as well. Some of the problems that are still persistent with LLMs are hallucinations. I'm sure a lot of you have heard about this. Hallucinations happen whenever models generate incorrect or nonsensical text. The models struggle from outdated data. For example, GPT-4 was trained on data up to April 2023. And a lot of times the relevant knowledge, and this is very use case specific, is not used. But there may be a solution, and I would like to introduce retrieval augmented generation, short for RAG. And this is quickly emerging as a modern accepted technique, as one of the best practices when it comes to building LLM applications. And it is a technique for enhancing the accuracy and reliability of generative AI models with facts fetched from external sources. So the typical RAG pipeline follows these 4 steps. So we would take the user's question, we would generate the embedding out of it, we would then use that embedding and go to our vector search database, run a similarity search to retrieve the relevant documents. We would then take the relevant documents, send it to package it up into a RAG prompt, send it to the LLM, and then have the LLM synthesize an answer back. So to visualize the whole RAG workflow, again, in this diagram, you see we get the question, we use that question, we generate an embedding, we go to a knowledge base, we retrieve the relevant knowledge, we take the relevant knowledge and the question, we send it to the LLM and get the answer back. So over the next couple slides, we'll look at what vector embeddings are, what similarity search is, and what the RAG prompt looks like. So what are vector embeddings? Vector embeddings are a machine learning technique to represent data in an n-dimensional space. The LLMs encode meaning behind texts in the embedding space, also known as the latent space. So for example, the phrase, the Ruby programming language is 30 years old and has stood the test of time. If we take that string and put it through an embedding function and put it through an embedding model, we will get an array of float numbers on the other side. For example, OpenAI, using the text embedding Ada 2 model, produces an array of size 1536, which means that there are 1536 float numbers. So as you generate embeddings for your data, it exists in the vector embedding space or the latent space, and it's clustered by meaning. So this is a 2D visual taken from a blog post where they cataloged and generated embeddings for 15,000 news titles. And you could see that the news titles that are similar to each other when it comes to a certain topic are all next to each other. So for example, the ones, the sport-related news titles are all clustered together. The politics and conflict ones are clustered together, the science and tech ones as well, etc. So this takes us to similarity search. which is synonymous with vector search or semantic search. And it is a search by meaning, not just a keyword search. When we're doing similarity search, we're taking our query, we're taking our embedding, and we're calculating the nearest neighbors. And you can use a different ways of calculating that distance. You can use the Manhattan distance, the Euclidean, the cosine, the Chebyshev. So this is another example similar to the previous slide. We're actually using Langchain.rb here to kind of illustrate this concept. So we have 3 strings here and 3 embeddings. So embedding number 1 is an embedding that we generate for a string. The Ruby programming language is 30 years old and has stood the test of time. Embedding number 2 is an embedding generated for Ruby is a safe choice for your technology stack. And embedding number 3 is an embedding that was generated for the string Express.js as a framework for building web services with Node. So you can see that we require the LangChain gem. We are using the OpenAI and its model to generate embeddings. And we generate the embeddings for those 3 strings. And you can see that we get back arrays of float numbers. And when we try to calculate a distance between embedding number 1 and embedding number 2, you can see that it's equal to 0.85, which is kind of similar. The scale is 0 to 1. Closer to 1 means more similar. And the distance between embedding number 1 and embedding number 3 is 0.75, which is less similar. So you could see how the way that the embeddings are generated, the data is structured, is clustered together, again, based on its meaning. So the last step is taking all of that and putting it into a RAG prompt. So in this case, we're using LangChain again to load the file from, load the prompt from the template stored locally. And when we call .format and pass those variables, we will get back a string, which is our prompt that will be sent to the LLM. So in this prompt, we have the instructions, which you would typically tell the LLM the format and the style of the response that you expect in your application. The context contains a collection of the relevant documents that were extracted during the similarity search from the vector search database, typically from a vector search database, although it could be any source, any data source really, and the original question. So when we try to put it all together, referring back to the McKinsey report earlier, generative AI technology could drive a lot of value across the entire organization. Number 1 target is revolutionizing the internal knowledge management systems. So McKinsey claims that knowledge workers spent about 1 day each work week searching for and gathering information. So if you could make that easier, there's a lot of value to be yielded. In this code sample, we're using the Google Palm LLM, and we're using the vector database. We're using the Chroma vector database, and we're setting the pointers or the paths to our files. And these are our generic corporate data, proprietary data. Market analysis produced by our business analysts, transcript with customers produced by our customer support representatives, product requirements produced by our R&D team. We're taking all that data, we're chunking it, we're generating embeddings for it, and we're storing it in a vector search database, in the Chroma vector search database. And once that's done, we can now ask Q&A style questions. For example, what kind of product features are we missing? What do our customers think about our product? What are our top product priorities for Q1 and 2024? Behind the scenes, we will run the similarity search, extract the relevant data from the vector search database, and then yield it back to the LLM to synthesize an answer. Building RAG systems is difficult. It takes a lot of trial and error to build a well-functioning RAG system. So number one thing that everyone does, step one, is human evals. So if you had used ChatGPT or similar systems, I'm sure you've seen the upvote, downvote on the response that the LLM gives you. This is then sent back to the OpenAI team, and this lets them track quantitative data to evaluate whether the response that the LLM is giving to the user's question is accurate or not, or what the user expects or not. There's additional metrics that are kind of emerging and additional techniques. There's research papers being published pretty much weekly on these topics. One of these techniques is the RAGAS metrics, and RAGAS stands for Retrieval Augmented Generation Assessment. And they define several different metrics, how you can quantitatively evaluate the effectiveness of your RAG pipeline. So some of the metrics they define are faithfulness, which is ensuring that the retrieved context can act as a justification for a generated answer. Context relevance, which is a metric to ensure that the context is focused with little to no irrelevant information. We don't just want to send as much data as possible. It's not going to be useful. Another metric is answer relevance. So making sure that the answer addresses the actual question. You can see we're using Langchain.rb. This methodology is implemented in our library. We're instantiating the RAGAS tool and then calling .score and calling the answer that the LLM produced, the question that was posed to it, and the context. So the slide was taken from one of the OpenAI presentations during the OpenAI Dev Day. They talk about helping one of their customers optimize their RAG pipeline and look at all the different things that they had tried. The initial iteration produced a 45% accuracy. They tried the hide retrieval methodology. They tried to use fine-tuned embedding model to produce embeddings. That didn't work. They tried different chunking and embedding experiments, and that yielded some improvement. They were up to 65% accuracy that the RAG system produced. They tried re-ranking the results, classification step, prompt engineering, tool use, query expansion, and with all of these consecutive iterations, very careful steps, calculated steps, they were able to get to 98% accuracy. TLDR, it's very difficult to build a well-tuned, functioning RAG system. So in this slide, we're calling this vector search DBs and LLMs matrix. We're supporting, the library supports a lot of different LLMs, a lot of different LLM vendors, and a lot of different types of vector search databases. The field is moving so quickly, we don't know which ones are going to survive, which ones are going to fold, which ones are going to be acquired, etc. So you can be sure that if you use Langchain.rb, you will be using the same identical APIs. There's a much lower vendor lock-in than if you were using some of these technologies directly, which gives you a lot of optionality. You can pair up any vector search database with any LLM. And lastly, what I wanted to cover was AI agents. And AI agents are autonomous or semi-autonomous general purpose LLM powered programs. They can use tools, and tools are basically APIs or other systems that the LLM can use. And agents work best with powerful foundational models. Although if you close in on its surface area of responsibilities, you can get away with using a lesser powerful model. And AI agents can be used to automate workflows, business processes, and execute multi-step tasks. And this is kind of the way I think about this, is if previously, whenever you would account for different flowcharts, you would have an input and you would code up all the different if-else permutations and different forks and branches that your application could go down. And now with AI, whenever you're building your flow control, you can account for a lot more ambiguity. You can account for all the different edge cases or various inputs that you've never even seen before. So I'd like to show a quick demo here of one of our AI agents. So let me play the video. So you could see we're using Google Palm as the LLM. We're instantiating the LLM client. In this case, we're going to be using the Google search tool and the weather tool. And these are simple tools that can call the Google search API or the weather tool or the weather API. So we're instantiating our React agent. We're passing it the LLM and the tools that it will have access to. So in this case, we're asking a simple question. Our question is, where did John F. Kennedy like to spend his summers, and what is the weather there right now? And as we run the agent, we can see the steps that the agent takes. So the agent receives the original prompt, and it decides to initially invoke the Google search with the following search query. Where did John F. Kennedy like to spend his summers? We execute the Google search tool on the LLM's behalf and give the response back. Send it back to the LLM. Then the LLM decides to execute the weather tool and find the weather for this specific location like we had asked it. So it invokes the weather tool with this input, Hyannis-Port, Massachusetts. We execute the weather tool on its behalf and yield back the answer to it. And the final answer from the LLM is that John F. Kennedy liked to spend his summers in Hyannis-Port, Massachusetts. And the current weather there is 40 degrees Fahrenheit, feels like 32.76. So, wrapping up. So we talked about how AI, by a lot of different estimates, is emerging as the centerpiece of each tech stack. We talked about generative AI and its different use cases, whether it's turning unstructured to structured data, or sentiment analysis, or classifying data, or summarization. We talked about a lot of its problems, main one being hallucinations. We proposed RAG as one of the industry accepted techniques for addressing some of those problems. We talked about what vector embeddings are and what similarity search is. We talked about the RAG prompt. We also talked about the evaluations, and in no way are the evaluations solved. There's still a lot of research being done. It's still not a solved problem, and I expect that there will be a lot of innovation in the future. And lastly, I want to say that Ruby is a beautiful community, and we ought to adapt and address the growing AI needs. Otherwise, we're going to miss the AI train. Thank you. Any questions? Happy to answer any questions. Thank you.